Welcome to Lesson 18 of Module 4. The title of this lesson is kind of long. We're still doing linear equations. The title of this lesson is There is only one line passing through a given point with a given slope. So that is one of the things that we're going to look at today, and we're going to actually look at a very short, simple proof of that, which is pretty intuitive that if two lines share a point and they share the same slope, they're actually the same line. But that's important for our goal of proving that the graph of a linear equation is indeed a line. Okay, so please excuse my voice today. It's better than it was yesterday, but it's still kind of froggy. So, so if you could open to your classwork, the opening exercise, we're going to look at the graphs here, A, B, and C and D, and your job is to examine each of the graphs and their equations below. I'm just reading the directions here. Identify the coordinates of the point where the line intersects the y-axis. Describe the relationship between the point and the equation y equals mx plus b. So these are all in the form y equals mx plus b, each of the equations. So take just a couple minutes to do that. Go ahead and pause the video, do A, B, C, and D, and then come back and we'll share. Okay, so for graph A, if I look at the line here, I can see the y-axis right here. Here's where the line crosses it, and it is at the value positive 3. So I could say the y-intercept, let me put it here, y-intercept equals 3. Okay, look at the next one. The next one, the y-intercept, you should have done these already, is 7. On C, now this one is crossing the y-intercept or the y-axis at a negative value, so the y-intercept is negative 2. And then on the fourth graph here, the y-intercept is negative, oh, that doesn't look very good, is negative 4. Okay, so hopefully you saw the correlation to the equations. Notice that we've seen that the coefficient of the x term, in this case negative 2/3, in the case of C, is the slope. And now we're going to see that this constant term that is added to the after mx is the y-intercept. Okay, so in y equals mx plus b, b is the y-intercept. So let's look at that. Remember, we have seen already two forms of a linear equation. We've seen the standard form, which we write as ax. Let me use some different colors here. We'll use purple for the variables. Ax plus by equals c. So that's the standard form of a linear equation. And we had some practice, but we probably need a little more practice transforming that standard form of a linear equation into what's called slope-intercept form, which is just y equals m times x plus b. Okay, so in the last lesson we saw that when we put the linear equation in this form, it's really nice because we can immediately know what the slope is, and we can immediately know one point, which is the point where it crosses the y-axis, and that would be the value of b. Now remember, I want to point out again that the b in the standard form and the b in the slope-intercept form don't have anything to do with one another. I mean, they're only related algebraically, so they are not the same number, so you can't use this b when we're in standard form. this b is not the y-intercept. It's only when you have it in slope-intercept form that this, this number here after the mx term is the y-intercept. Okay, so but remember, you can take an equation in this form and algebraically transform it by solving for y, getting y on one side and everything else over here. So we've done lots of that. Okay. So again, our goal over the last 4 lessons has been to prove that the graph of a linear equation in 2 variables, the standard form ax plus by equals c, is a line. So we've plotted lots of points and we've said, gee, it sure looks like it's a line. But proving something requires a little bit more analysis. So we're working towards that. And you're not expected to reproduce these proofs, but it's good for you to be exposed to it. You're going to be doing lots of proofs as you move on in math. Okay, so there were 4 things we needed to show in order to prove that the graph is a line. So the first one is that there's a way to measure the steepness of a line, and we're calling that slope or rate of change. So we use those terms kind of interchangeably. The slope is the rate of change. Okay, and when we did that in lesson 15, we defined that, and we'll look at it again today. Any 2 points on a non-vertical line can be used to find the slope. So we saw that, I think, in lesson 16, and we saw by using similar triangles that no matter which 2 points we use on a non-vertical line, the slope is the same because those ratios of the similar triangles are equal. The third thing we needed was to show that the line joining any 2 points on the graph of y equals mx plus b has slope m. We did that in the last lesson, and then in this lesson we're going to show that there's only one line with a given slope through a given point. And with those 4 things together, we'll be able to construct a simple proof in the next lesson that the graph of a linear equation is a line. Okay, so let's do a quick review of what that number slope is. So if we have this line, we'll call this line L. If I want to measure the slope of it, I'm going to define 2 points on that line, and I'll have P, call them P and R. And remember, I can use any 2 points on a line to find slope. They don't have to be specific points. And I'm going to draw a line parallel to the x-axis going through P and parallel to the y-axis going through R. We'll call this intersection our point Q. And so think for a minute, see if you can remember what ratio are we using to come up with this number for slope. Okay, so if you said but slope is the length QR, which is also the vertical change in position. This is length QR. That doesn't look very good. Divided by length QP. And that would be this distance here. So what we have is we have the vertical change divided by the horizontal change. So if a line is very steep, it's going to have a lot of vertical change for a little bit of horizontal change, which, you know, from fractions or ratios, that when this number gets really big and this one is smaller, that this overall number is bigger. So the steeper slopes have a bigger number, which is why we're defining it as this ratio. So remember, if we used different points to find the slope and had a different slope triangle, we'd be able to show that all those triangles would be similar by the angle-angle postulate. And so this ratio is the same for any 2 points on line L. Okay, so in example 1, we're going to use what we know about slope as a ratio and the y-intercept to graph these equations. So previously, you would have made an xy table, maybe chosen some values for x, computed the values for y, put them on the graph, and connected the line. And that's fine. There's nothing wrong with that. But when the equation is in this slope-intercept form, and you can find the slope and the y-intercept so quickly, there's a quicker way to graph. So we're going to start by naming the slope and y-intercept. So for this equation, the slope is 2/3. Remember, it's always the coefficient of the x term. And the y-intercept is that number b, in this case 1. Okay, so we can start by graphing the y-intercept right there at 0, 1. And then to get another point, we're going to use the slope. So remember, this slope is equal to that ratio of the change in y over the change in x. Okay. Lots of different ways to think of it. It's the vertical rise over the run. So what we're going to do is we're going to look at how to find that next point using the slope. So with the slope of 2/3, the horizontal change is 3 and the vertical change is 2. So in other words, for every 3 that I go over, that line is rising 2 units. So by doing that, I can plot another point. And I could plot more using the same technique right here. So anyway, once you get that second point plotted, then you can draw your line. Let's see if I can make this go through here. So my line is roughly right there. Nope, that's not good. Okay, that's a little better. So I didn't have to compute any x, y values. I just plotted the y-intercept and then used the slope to find another point. So that was a pretty quick way to draw the graph of a line. Okay, let's look at another example. We want to graph the equation y equals -3/4 x minus 2. So name the slope and the y-intercept. So the slope is the coefficient of the x term, so it's -3/4. And the y-intercept, in this case, now notice I have -2, but the equation is y equals mx plus b. So I kind of want to think of this -2 or -2 as plus a -2. Okay, so you can kind of think of it that way. So the y-intercept here is equal to -2. So we can go ahead and plot our y-intercept. That's where we want to start with our known point. So y-intercept is -2 right there. So that's where it crosses the y-axis. Our slope is -3/4. So when I look at these ratios, I want to always associate the negative sign with the numerator. It's just a little easier to think about it that way. So maybe you'll see why here. So I'm gonna go. So my horizontal change is 4. So I'm gonna come over here 4. 1, 2, 3, 4 units. And my vertical change is -3. So I want to come down 3. And a good check for yourself is always, you know what a negative slope looks like. It goes this way through a graph, whereas a positive slope goes this way. So if I had gone up from there 3, that would have been a positive slope. but I want a negative slope. So I've got to go down to find the next point. So let's go ahead and connect that line. So connecting those 2 points, I get this. So this is the graph of y equals negative 3/4 x minus 2. Okay, let's look at another example. The graph of this equation is y equals 4x minus 7. So our slope m is equal to 4. Again, it's the coefficient of the x term. And our y-intercept is negative 7. Okay, so once again, we're going to start with the y-intercept. So let's go ahead and graph that way down here. Negative 7. Right, is that right? Yeah, negative 7 right there. That's where it crosses the y-axis. And we're going to use a slope of 4. Okay, so this 4 isn't written as a ratio, so what you might want to do is express it as a ratio. So 4 can also be thought of as 4 over 1. So for every 1 unit in the horizontal direction, this line's going to rise 4. So that slope triangle would look like this, come over 1, and up 4, like so. So we can put another point right there, and then draw our line. I can't get it in the right place. There we go. So there's our 2 points. And we can draw the line. So when the slope's a whole number, just remember to express it as a ratio so that you can get that horizontal change there. So my line would look something like that. So a double check, it's a positive slope, which is what I have there. It's a pretty steep slope with a number 4, as opposed to some of the earlier examples we had. Let's look at a positive one. This is 2/3, so it's not near as steep as a slope of 4. Okay. Okay, now you can try it yourself. Work on exercises 1 through 4. Stop after exercise 4, and we're going to have a little discussion. And then we'll go back and do 5 and 6. So work on exercises 1 through 4, answer all the questions. The graphs are there for you, the coordinate grids to use. So here's, turn the page to find the one for exercise 1, and go all the way up through exercise 4. Okay. Okay, now I'm going to just quickly go through the results for exercises 1 through 4. They're just like the examples we just did. So pause the video as needed to check your work. So for 1, the slope would be 5/2, the y-intercept negative 4, and the graph would look like this. The slope of 5/2 has a vertical rise of 5 for a horizontal length of 2. And so there's the slope. We graphed the negative 4 y-intercept, and the other point using the slope. Okay, so for exercise 2, the slope is negative 3 and the y-intercept is 6. Now notice I'm using a convention just to write a number for the y-intercept. Sometimes the y-intercept is written as the coordinates of the point. So 0, 6 would be the coordinates of that point. Okay. So I'm graphing 1 point. That's the y-intercept at 0, 6. And then I use the slope of negative 3. So negative 3 can be thought of as negative 3 over 1. So there's my horizontal distance over to that point Q, and then down 3 gives me my slope of negative 3. And again, remember, had I gone up, I would have ended up with a line with positive slope, but this line has a negative slope. Okay, exercise 3 is the equation y equals 1x plus 0, which is actually just the equation y equals x. So on that line, the y coordinate and the x coordinate of every ordered pair should be equal, right? That's what y equals x would mean. So, but the slope of that line is 1, the y-intercept is 0, so that means the y-intercept is at the origin. It goes through the point 0, 0. And this is what the graph would look like. Using a slope of 1, we can think of that as 1 over 1. So it goes up like that. Okay, so let's look at exercise 4, which was a little bit different. You were just asked to graph the point 0, 2. So we're graphing a point, that is the y-intercept, and find another point on the graph using the slope m equals 2 sevenths. So you can see here I use the slope m equals 2 sevenths, a horizontal change of 7 with a vertical change of 2 to get another point, and we connected the points to make the line. So you're asked in part C of that to draw a different line that goes through the point 0, 2 with the slope 2 sevenths. And what do you notice? Well, so hopefully you notice that if you try to draw a different line going through this point with this slope, it's going to be exactly the same line. You can only draw one line. Okay, so we're going to look at just a simple proof of that idea right now. And you don't have this in your notes, so you can just follow along and jot down some notes if you'd like. So for this proof, we're going to use something called proof by contradiction. So I'm going to draw myself a line. We're going to call this line L. And it goes through a certain point here, right there. And we'll call that point P. So there's point P on line L. And I'm going to make an assumption, which is wrong, but I want to contradict myself, that I can draw another line through point P, and we'll call this one L prime, that has the same slope, but is a different line. Okay, so that's what I've drawn. I'm assuming that L and L prime have the same slope, okay? So I'm going to come over some distance, a vertical distance here. Let's get a different color for our line. Come over here, parallel to the x-axis. And from there I'll draw another line going up parallel to the y-axis. So this is going to give me my point Q right here and some slope triangles. So what I'll notice is that we're going to label the intersections here. So this would be point R on line L, and we'll call this point R prime on line L prime. Okay, so now we have, now we can define our slope. So the slope of line L would be QR, the length QR, over the length QP. So that would be this length here, QR over QP. So that would be the slope of line L. Now we're saying that the slope of line L prime is the same, so I'm just going to use M again. So the slope of line L prime is length Q R prime over length QP. Okay, so since we started out by saying that these two lines had the same slope, then I'm saying that this ratio and this ratio are the same. So what that means is that length QR is equal to length QR prime. And since that's true, what that means is that R prime and R have to be the same point here. And the way I've drawn this can't be right. So there can't be two lines going through a given point with the same slope. They would be the same exact line, just a copy of itself. All right, so continuing on with this idea of linear equations and slope and rate of change, I want you to work on exercises 5 and 6 by yourself or with somebody, and then come back, pause the video, do that, and come back and check your results. These are a little trickier than the others because these put slope in the context of the first one. Number 5 is a bank account, a savings account, and number 6 is a road trip. So this will involve speed. Okay, so go ahead and work on those and then come back and check your work. Okay, so I'm going to talk you through my thinking on this problem, and then, but I'm totally open to the fact that there's lots of ways to do this, but I like to make sure, first of all, that I know what my variables are. So the total, Y is the total amount of money in my account, and X is the number of weeks that I've had the money there. And so I want to write an equation that describes that situation. So the way I would start with this would just be to write a verbal model. So my total amount in my account is going to be my weekly savings plus my starting point, because I started with $10, plus my starting dollars, I could say. Okay, so my total amount by my variables is Y, and then my weekly savings, if I want to think about writing an expression for that, I save a certain amount each week, and then I multiply that by the number of weeks that are there. So the number of weeks is X. So I need to know how much is it that I'm saving each week. Okay, well, I can see that I started with 10, and 8 weeks later I had 24. So in 8 weeks, I saved $14. And I'm going to divide that by 8 weeks because it says that I can assume that I save the same amount each week. So that's kind of the constant rate part of this problem. So 14 divided by 8, I'm going to simplify to, let me get my pen back, to 7 over 4. So if I think of that number 7/4, what that's telling me is that I'm saving $1.75 each week, because this is 1 3/4 per week, right? So, but I'm going to use 7/4 because that is my rate of change. If you think about it, the rate of change in my savings account is how much I save every week. So I'm gonna put that number in here. It's just a different color here. So this is 7/4 X. So that's my weekly savings. So if X is 1, then I've saved $1.75 in addition to my 10. If X is 8 times 7/4 is going to be my $14 that I saved there. So this expression 7/4 X is my weekly savings. Okay, but I started with 10, so I've got this plus $10, plus 10. So there's my, and notice that just writing it like this, it's already in slope-intercept form. Y equals 7/4 X plus 10. So the slope is the coefficient of the X term. So the slope is 7/4. And the y-intercept equals 10. It's going to be the point 010 on the graph. Okay, so the y-intercept is 10. So I'm asked, what do these numbers represent? Well, slope is the amount saved each week. Okay, which becomes my rate of change of my balance in my savings account. And the y-intercept is what I started with. Y-intercept is my starting point. Okay. All right, so now I'm asked to graph this equation on the coordinate plane. So let's get a known point on there. I know that at week 0, I had $10. So I'm going to put that point right there. Okay, so 0, 10. I know something else. I know that 8 weeks later, I had $24. So I can just go ahead and put that point on. $24 at 8 weeks, right there. And then I could draw the line through there. But I could try putting another point on. If I use my slope to find another point, my slope is 7/4, so that means I'm going to go over 4 units. Get a better line than that. Over 4 weeks and up $7 basically. So, but I've got to look at my my scale carefully. Each of the lines on the vertical axis stand for $2. So to go up $7, I'm going to go 3.5 of those and put a point right in the middle. Right in the middle right there. Okay, those points appear to be in the same line, so we're going to try to, let's see if I can connect them. So there's a line representing the situation of the total amount of savings in my bank account. Okay, so we have one more question here. It says, could any other line represent this situation? For example, could a line going through the point 010 with a slope of 7/5 represent the amount of money you saved each week? Explain. So you should have said something to the effect that the slope of 7/5 wouldn't represent this situation because that's not the amount that was saved each week. So that would end up only saving less than $24 at the end of 8 weeks. And so there wouldn't be another line to represent this situation. So that's getting at the idea that if there's a given slope or rate of change and a given point that you're starting with, there's only one line through that slope. Okay, let's look at number 6. Okay, so number 6 again is having to do with distance and rate and that kind of thing. So we're on a road trip. We've gone 120 miles. They continue the trip and drive at a constant rate of 50 miles per hour. So every hour, they're adding 50 miles. So they've already gone 120. So after 1 hour, they would have gone another 50 or 170. And after another hour, 220. So we're going to use the variables that are defined. And I've written so that my total distance is equal to the additional miles they travel plus the original 120 miles. So I'm told that total distance is going to be represented by the variable y. So I just need an expression for the additional miles they travel. So they're going 50 miles every hour, and x is the number of hours. So that expression is going to be 50 times x, and that's going to be added to 120. So notice we have our slope-intercept form right there. So the slope, m, is 50, and that number represents their rate or their speed in miles per hour, okay? And then the y-intercept equals 120. So that was kind of their starting point. Okay. So we can graph this equation on the coordinate plane. And so our y-intercept is 120. So it'd be right here. Right there at 0 hours, they're already at 120. So I know that every hour I'm adding 50. But I'm going to go every 2 hours. I'm going to use a different slope triangle because I know that in 2 hours they'll add 100 miles to their trip, and so they will have gone 220. And the reason I'm doing that point is because it's at one of the grid lines. It's a nice point, so I can put it right there. If I wanted to do the 1 hour and add 50, it would be right in there. So I could have done that one too. And then I'm going to connect that. So connecting that into a line, I can see a line that represents this situation. So part D says, could any other line represent this situation? For example, could a line going through the point 0, 1, 20 with a slope of 75 represent the distance the friends drive? And the answer to that would be no, because that would be a situation where they were going 75 miles an hour, but they're going 50. So you should write something that represents that. Okay, so in both of those examples, we saw how we can use the context of a problem, either a road trip with a given speed or a bank account with a given amount saved each time period, and write an equation in slope-intercept form. All right, so let's look at what we've done, what we learned in this lesson. Just a quick recap. So we learned that for the equation, linear equation in the form y equals mx plus b, which we're calling slope-intercept form, that 0b is the location where the graph intersects the y-axis. And we also saw how we can graph a line using a point, and the point that we used was the y-intercept and the slope. So we could graph a line without having to construct an XY table and solve for some ordered pairs. So it's just another tool that you have. We know also, because we proved it, that there is only one line with a given slope passing through a given point. Okay, so that's lesson 18. Good luck with the problem set on that, and we'll see you back here for lesson 19, where we're going to pull all of this together in a proof that the graph of a linear equation is a line.